I'm going to show you a pattern that if you saw it for the first time, you would think had to be a trick. Pick any irrational number you want. Pi works, the square root of 2 works, the golden ratio works, anything irrational. Now take a circle, walk around it, but instead of walking the full way, walk only a fraction of the way, specifically alpha of the way, where alpha is your irrational number. Mark where you land, then walk alpha again, and mark again. Walk alpha, mark, walk alpha, mark. Keep walking, keep marking. After 10 steps, you have 10 marks on the circle. After 100 steps, 100 marks. After 1,000, 1,000. The marks look random. They never repeat. Alpha being irrational guarantees that. They don't fall on top of each other. They don't form any obvious clusters. They fill the circle in a way that looks like a slow scatter. If you measured the gaps between consecutive marks, the lengths of the arcs between adjacent marked points, you would expect those gaps to be all kinds of different sizes. After 100 marks, why wouldn't you have 100 different gap sizes? Some long arcs, some short, some medium. A wild distribution. That is the wrong expectation. The gaps take at most 3 distinct sizes. 3. Not approximately 3. Not 3 plus some error. At most 3. For every irrational alpha. For every number of marks. This is called the Three-Distance Theorem. And once you see it, you cannot unsee it. Let's actually watch it happen. Start with a circle, drop a point at the top, call it position 0. That's the starting mark. Now rotate by alpha, drop another point. The circle is divided into 2 arcs, a small one and a large one. 2 arcs, 2 gap sizes. Rotate by alpha again. A third point lands. It lands in the larger of the 2 existing gaps and splits it into 2 pieces. Now you have 3 arcs. The gap sizes, there could be up to 3 of them. Rotate again. The fourth point lands somewhere, splits some arc, gives you 4 arcs. How many gap sizes? 2 or 3. Always. Keep going. 5 points, 6 points, 10 points, 100 points. The number of arcs grows by exactly 1 each time. The number of distinct gap sizes stays at 2 or 3. Never 4, never more. This is wildly counterintuitive. Adding a new point splits an existing arc, which creates 2 new arcs whose lengths depend on the value of alpha. Yet somehow, the new arc lengths are always equal to lengths that already existed somewhere in the system, or they introduce just 1 new length. The system is constrained. The constraint comes from a hidden structure inside alpha, the structure of its continued fraction expansion, which we'll get to. But the result, the observation that any irrational rotation produces at most 3 gap lengths, is the punch. To appreciate why this is strange, compare it to a different scenario. Suppose, instead of rotating by a fixed amount alpha, you dropped points on the circle randomly, uniformly distributed. 100 random points. Now measure the gaps between adjacent points. You will get, with overwhelming probability, 100 different gap sizes. There is no reason for any 2 random gaps to be equal. The expected number of distinct gap lengths grows linearly with the number of points. For random points, many distinct gap lengths. For irrational rotation, at most 3. The contrast is sharp. Rotating by a fixed irrational angle does something fundamentally non-random. It distributes points in a way that statistical tests would barely distinguish from uniform, but the underlying structure has constraints that random points do not have. Here is one way to feel it. Mark the first 1,000 points of rotation by pi divided by 10. The marks visit the circle in a specific, completely deterministic order. The order is determined by the integer parts of alpha, 2 alpha, 3 alpha, and so on. For random points, the order in which they fall is itself random. For irrational rotation, the order is determined, and the cost of determinism is that the gap distribution is constrained to at most 3 values at any moment. Here is the precise statement. Take any irrational alpha, take any positive integer n, Place the endpoints alpha, 2 alpha, 3 alpha, all the way through n alpha, all taken modulo 1, on a circle of circumference 1. Sort them around the circle, measure the arc lengths between consecutive sorted points. The set of distinct arc lengths has at most 3 elements. That is the theorem. 2 or 3 distinct lengths, sometimes 2, sometimes 3, never more, never different. There's a slightly stronger statement. When there are 3 distinct lengths, the largest equals the sum of the other 2. Always. The 3 lengths are not arbitrary. They satisfy a rigid arithmetic relation. Hugo Steinhaus, a Polish mathematician, conjectured this around the 1950s. The first proof was given by Vera T in 1957. Other proofs followed shortly after, by Stanisław Świerczkowski and by Norbert Slater. The theorem became known as the Three-Distance Theorem, or sometimes the Steinhaus conjecture. It is elementary. The proofs use no advanced machinery. You could explain it to a clever high school student. But the result feels miraculous when you first see it, because adding a point should give you a new arc length, and yet the new lengths land back inside a set of at most 3 options. It is one of those theorems that, once stated, looks obvious, until you try to prove it. The reason the gaps stay constrained is, in one sentence, each new point you add inherits its structure from points already there. When you rotate by alpha and add the n plus first point, that new point lies in some existing gap. It does not land in any gap. It lands in a specific one. Which gap depends on the algebraic structure of alpha. For example, there is always a unique youngest gap on the circle, the gap that was created most recently. When you rotate by alpha and place the new point lands in the youngest gap, and it splits that gap in a specific ratio. That ratio is determined by alpha. As you keep adding points, the ratio acts again and again on the youngest gap, producing a recursive structure. The recursion is finite state. There are only a small number of distinct gap lengths it can produce, at most 3. This is the engine. The dynamical system rotate by alpha and split the youngest gap has a memory of length at most 3. The system cannot produce a 4th distinct length without first eliminating one of the existing ones, and when that happens, you're back to 2 or 3 lengths again. The proof is essentially a careful tracking of which gaps split into which other gaps, and showing that the gap length tree has only 3 live branches at any moment. The 3 gap lengths are not arbitrary numbers. They are tied directly to the continued fraction expansion of alpha. Every irrational alpha has a unique continued fraction expansion. For the golden ratio, the expansion is 1,1,1,1, repeating forever. For pi, the expansion is 3,7, 15, 1, 292, and so on. The continued fraction is a sequence of integers that characterizes alpha. Truncating the continued fraction gives the convergence, the best rational approximations to alpha. For pi, the convergents are 3, 22 over 7, 333 over 106, 355 over 113, and so on. The denominators of these convergents, 1, 7, 106, 113, 33,102, are exactly the values of n at which the gap structure on the circle changes. The three-distance theorem is not just an abstract curiosity. It explains real-world phenomena. Consider how plants arrange their leaves. Many species, sunflowers, pinecones, pineapples, Romanesco, exhibit phyllotaxis. Each new leaf or seed grows at a specific angle from the previous one, rotated by what's called the golden angle, 2 pi divided by the golden ratio squared, approximately 137.5 degrees. That angle is 2 pi times an irrational multiple. In the language of the theorem, the seeds of a sunflower are placed at angles 2 pi alpha, 2 pi times 2 alpha, 2 pi times 3 alpha, where alpha is 1 over the golden ratio squared. By the three-distance theorem, the angular gaps between adjacent seeds in the head of a sunflower take at most 3 distinct values at any stage of growth. Because the golden ratio has the most irrational continued fraction, all ones, the gaps stay almost equal to each other. That equality is why sunflower seeds are packed so efficiently. If the plant chose a rational multiple, seeds would align in radial lines and waste space. If it chose a generic irrational, gaps would be uneven. Only the golden angle, sitting at the deepest end of the three-distance regime, optimizes packing. The three-distance theorem is what tells us why. Plant biology, evolutionary pressure, and number theory converge at the golden angle. So this is what the three-distance theorem says. Irrational rotations on a circle, despite looking arbitrary, produce a tight, predictable structure. At every step, the circle is partitioned into at most 3 distinct gap lengths. The number of arcs grows linearly. The lengths themselves jump at the convergence of alpha's continued fraction. The deepest case, the golden ratio, corresponds to the most uniform possible distribution, and that's the case nature picks for arranging seeds and leaves. Hugo Steinhaus, the Polish mathematician who conjectured the theorem, was famously eclectic. He worked on measure theory, on probability, on the Banach-Tarski paradox. The three-distance conjecture was one of many short, almost recreational problems he proposed in the 1950s. He posed it. Vera T proved it within a year. Today the theorem is a standard tool in dynamical systems, in computational geometry, in the analysis of low discrepancy sequences for quasi-Monte Carlo methods. But it remains in its essence what it was when Steinhaus first wrote it down. A one-line statement about points on a circle, with a proof that fits on one page, and a conclusion that nobody believes until they see it. Take an irrational number, rotate, mark, count the gap sizes. There are 3. There will always be 3.